someone decided the idea was clear. We need knowledge of phenomena. We want to model with sophisticated models something. We need to know what we're doing. And as Stelios is experimentalist, and he knows that for exotic phenomena, when he gave me two possibilities, I've chosen the most complicated one. So he has to work more. Moreover, as the group, Italian group in MEMOCS, most active is the one studying instabilities. I don't, studying the instability of a two-dimensional system is already complicated. Studying instabilities in continuous systems is much more complicated. So challenging problems from phenomenology. So Stelios will talk at least 45 minutes and then we will have open discussion. Okay?
50 minutes.
50.
Thank you.
Angelo is a German Napoleon. Stelios is a German Cypriot.
Put it over there. I don't want to use it. So, thank you. I am not going to use the microphone, and I hope it's okay. I'm going to have a fight with it. So thank you, Francesco, for inviting me. I can tell you that when he first contacted me, I felt a little bit that I might not really be the best person to contribute to such a distinguished group of theoreticians. But after a couple of communications on Skype, as you already know, he's a very convincing guy. So here I am. I also, as he said, I gave him two subjects. One that I could go into detail with some equations, numerical stuff, experiments, and describe the physics in detail. And then I gave him another one, and that's the one he chose. And this really is a very difficult talk for me to give, and I hope that that it is appreciated because it's a mosaic of a number of subjects that at first definitely their physics, each one has its own physics, and they don't seem to be related, but they have a relationship in that they develop an instability that localizes and then it propagates, and that's really their common thing. So I'm going to go through. Unfortunately, each one has a history. Some of them go back maybe 15 years, but I'm just going to give you a little bird's eye view, primarily concentrating on the similarities and on the physics. Very few equations. I don't usually apologize for that, but for this audience I think it's better to put it at the beginning. So the underlying connection with these problems is quasi-static response under load. I said here it can be tensile, it can be compressive, it can be pressure, it can be whatever. That is like this. This here is, so this is load, this is some generalized deformation. There is a stable regime. The material or the structure deforms homogeneously. There is an instability. The instability can be of a limit load type, it can be a bifurcation, but it's an instability that leads to localization. localization for us here is going to be some localized deformation that develops, grows, comes to a certain point and stops. And that's really the difference of this class of instabilities from others that may lead to catastrophic failure. So it stops for some reason, and each one of the systems is going to have its own reason for arresting the local deformation. And after that, if you have a large enough domain, it can propagate, and under quasi-static loading, it can propagate and generate a plateau. When all of the material is deformed to this higher deformation, then we return to homogeneous state again. I think maybe this is my connection with the audience here. Okay, so this is what is behind this type of phenomena, and I call it underlying. I am not a tremendous person for formalisms. That's a word that I think is representative. Load, deformation. There is an underlying response of the system that has this up, down, up behavior, and at least a lot of you, I think, are familiar with Abeyratne knolls and shape memory metals, and sort of that is what is underlying the phase transformation in that case. And for systems that we can reproduce this somehow, there is the equal area of Maxwell that Ericsson proposed quite many years ago, and that equal area represents the load at which it propagates, the instability. Now, I'm going to start with this simple problem, which is not a material one, but it's a structural one, and it's the blowing up of a balloon. This is a rubber balloon, and the reason that I'm introducing it is because here we can see all the details as you're going to see. So it's a long tube. It's some kind of rubber. Okay, we inflate it, and at some stage a bulge develops. So that's the instability. This bulge grows. And at some diameter, when it reaches a certain length and a certain diameter, it stops growing diametrically and it starts propagating along the length. And then you have this situation that you see here, okay, where you have coexistence of a large deformation regime and a small deformation regime. And that's pictures from experiment. The instability develops as is shown here. I mean, I'm not going to be able to tell you exactly why in each case. Okay, so this is pressure, this is time, then this is an experiment. Okay, so here is the staple branch. When the deformation is uniform along the length, we reach a maximum, okay? And then there is a little jump here, depending how you inflate it, there is a little jump, and then you see the configurations that correspond. It grows, okay? Now it has, here is not in the picture anymore, it stops growing diametrically and starts spreading along the length, and it does so at a constant pressure. In this problem, we can recover this underlying response as follows. It's a membrane calculation of this rubber-like material I don't know if you can see it back there, but this is a stress, okay, and this is a stretch. So in the uniaxial test, this is what the response looks like. So you inflate this membrane, but you constrain it. Okay, it's not a long one. It's a plane to remain uniform along the length. And if you do that, then this is what you get. And the instability is a limit load instability. It comes down and then picks up. And the reason it picks up is that, and of course, here is the diameter, the small diameter, and here is the large diameter. And the reason you have this up in this case is because the instability occurs somewhere here. Okay? The reason that it picks up again is because the rubber stiffens as you stretch. These are large numbers of stretch. Okay? So and then if you do this Maxwell construction, the is equal area, something like this, one of the few equations I'm going to show, then you get the propagation pressure, and it is exact, perfect agreement with experiments. If you want to do more, then you need to do more work. Okay, so this is now a numerical solution of an axisymmetric membrane, but it's a long one, and you allow it now to develop the instability. Here it is. Here is this bulge growing, and you are going up this curve. Okay, there is a limit load instability here. It starts to come back. Okay, this instability develops this cusp. This is very, very bad instability. Okay, develops this cusp, and the extent of this cusp depends actually on the length of the structure that you have. And then after that, you see that I don't know if it's very clear back there. You see that the bulge grows, reaches a certain diameter, and then it propagates, steady state. The pressure remains constant. That's the Maxwell pressure. And then once you reach the end, then it starts inflating again uniformly, the whole thing. So there is what you get experimentally, and that's what you can get numerically in this case. Propagation pressure, like I said, you can get it in that case from the simple calculation that I showed you. All right, so now that's to introduce the subject. So now I'm going to go to some materials systems that exhibit this phenomenon, and I have prepared a few movies for you, and I'm going to show you what happens to this honeycomb. This is an experiment. It was the first material system that we investigated in the 90s, late 90s, and that is what happens. In a minute, I'll show you what load you record. So it's a honeycomb. The cells is polycarbonate. It's a hexagonal packing. Okay, I chose this at that time because the geometry was regular, as regular as it can get, and it could provide us a clearer picture of what was happening. The work actually was motivated by Gibson and Ashby's book on cellular materials, and honeycombs loaded in this way, in the plane, have been models for the more complicated three-dimensional forms that I'm going to discuss in a minute. because they provide a nice visualization framework, and as you can see, what we have is two deformation regimes. We had an instability. I'll show it to you again. We have an instability that causes a localization, and then we have this spreading, and that spreading, okay, it's occurring in a nice, more or less constant load. I will show you the instability again. That's the instability. Okay? It's a shear type of instability. It's a bifurcation in this case, and it causes localization. Why does it stop? It stops because the cells locally come into contact with each other, and nothing more can be done there. And then it continues. Okay, so that's movie one. So regarding what the load looks like, just a second. That's what the load looks like. It's not a total flat plateau because this system has some discreteness. Okay, it's not very large. It's a bumpy thing. Each one of those bumps corresponds to a zip and a zap of the cells. Okay, but okay, you can see it's very similar to what we saw earlier with the balloon. And when you crash the whole thing, then the load goes up. Then you can crash it a little bit more, perhaps. Now, yeah, let me return to. So, here, I know you guys like continuum theories, okay? I am a discrete person, but maybe I can motivate you to use your continua to analyze these challenging problems. So here you see the onset of the instability, and it can be predicted by taking a representative. This has periodicity in it, so you can extract the characteristic cell, and you can establish the bifurcation, or if the material is rate dependent like this, with a little imperfection, establish the beginning of the instability. So the onset of the instability here is a bifurcation, like I said. It can be obtained relatively easily from analyzing a characteristic cell, and beyond that, though, you have to work hard, or we had to work hard in order to go further. And that work resulted in what I'll show you now. So this is a finite element simulation. Okay, so finite element simulation of the crashing process. Let me stop for a second. The material is elastoplastic. It's viscoplastic, actually. There is each one of these cells is modeled with 23 finite elements. There is, of course, you can see geometric nonlinearity, significant large deformations, and the worst part is the contact. There is contact that stops it, and if you put all that stuff together, then you can reproduce it. Is there a way to get this from more continuum theories? That's the question, I think, for you. Now, so that's problem number 2. Before I go on, let me just say that actually you can get the up-down-up if you forget for a short time the rate dependence. You can use a characteristic cell again and get this up-down-up, and you can extract the limit, the Maxwell construction. The average of that plateau that we saw also from a relatively simple calculation, a smaller calculation. And there is the agreement between experiment and analysis. If I'm giving you the impression that these are very easy things, they are not. Okay, I mean, each one of these problems is 1 or 2 PhDs that I'm showing. Okay, now this is the bigger brother in the family. Actually, this is now foams, something that we have been doing in the 2000s, and I have chosen to show you how a foam made of aluminum behaves under compression. The microstructure, you can see it. Okay, I'll show you more detail in a minute. This is a relative density. It's about 8%. That means 8% is solid and the 92% is air. And if you compress it, okay, then this is how it crashes. I don't know again if you can see it very clearly. It has a linearly elastic regime. The cells deform uniformly. There is a little instability. It's a limit load in this case. There is localization we're going to see in a minute. And then there is a flat plateau. When most of the material is crushed, you enter this stable regime again. It's called densification for the foam mechanicians. Now, this is an X-ray tomography of a piece of this material, okay? In order for you to see the microstructure, it's cellular. The cells are polyhedra, very irregular, but for this material, the cells, it's monodispersed for those that are in the game. The cells are about the same volume, have about the same volume. I call these ligaments, not struts. The ligaments are like here, you see, again from X-ray tomography. That's what they look like. They like dog bones. And the reason they look like this rather than plateau borders is because the way this particular foam is manufactured. And you see that there is a variation in the cross-section. These are important ingredients if you want to do micromechanics, and that's really what we do. It's how does it crash? This is a particular experiment. It's not totally flat because there is some variation in relative density through the specimen. Specimen is about 100 millimeters tall and about 50 millimeters in diameter, 50 by 50 millimeters square. Stress, this is the shortening divided by the original height. Okay, but what was special about this? We have a poor man's, a small X-ray tomography that is tabletop, and we could not do the experiment in situ. So what we did is we loaded it. This is an elastoplastic material, so you load it and you reach a certain deformation. We unloaded and then took a scan. Okay, so this is an experiment that took 2 weeks actually, because the scan for us was 24 hours. But again, you see this general sort of response, and from those scans, this is now the tomography gives you the full field, right? Deformation, and we choose a slice through the depth. And this is 50 by 50 millimeters, and you see what happens. it's crashing. It's similar to what we saw earlier more clearly for the 2D case. It's, I have more details, but I don't have them here. The cells locally buckle, crash, the ligaments come into contact, the local crashing stops, and in the meantime the neighborhood gets destabilized, and then in that sense it propagates. Now, where it starts first, there is no preferred orientations. If anybody is looking for any special inclinations, it occurs where there is the biggest weakness. It's a random form, so there are weaker spots, and the profile of these bands is 3D through the specimen. Okay? As we continue loading, more cells crash, and then gradually the crashing zone moves upwards in this case. It could be downwards in another case. But I notice again that what we have, uncrashed material, crashed material. This is the characteristic of the propagating instabilities. The first approach that we took about 5 years ago was to model this, idealize a little bit the geometry. We were helped by the fact that the volume of the cells doesn't change, is monodispersed. So we idealized the microstructure like this. This is the Kelvin cell, but we introduce ingredients from what we measured. That means we have the correct density, that means we have some anisotropy, and then the distribution of the material along the ligaments came from measurements that we made. Now, once you regularize this, you have a characteristic cell, and you can again get something. You can get most of the properties, the elastic properties and the onset of the instability, but you cannot get the crashing. In fact, the elastic properties, there are plenty of them here because it's anisotropic. You can get them from quite simple beam models of the characteristic cell. The material response, the base material is shown here. It's an aluminum, okay, that's what it looks like. And if you put those into a characteristic cell, so this is a calculation of a characteristic cell that is fully periodic, okay, and you crash it, then this is what you get, okay? The stress, the change in height, okay, elastic behavior, okay, inelastic behavior, and a limit load. For this problem, for this material, for this microstructure, the instability is limited to one cell, as opposed to other materials that we have looked also in the past, where other instabilities are involved, are the dominant ones, long wave instabilities, or instabilities that involve more than one cell. And those types of calculations, he's maybe a connection with the community here, those type of calculations we have done with help actually from Professor Triantafylidis with block wave theory. That's the extent of homogenization that has been done in these problems. But like I said here, you analyze one cell and you get, that's the dominant behavior, and you get this limit load, and that's the strength of the material. If you want to get the plateau and the extent of the plateau, then in our case we had to work much harder. And instead of showing to you the solution that we obtained from the Kelvin cell, I will show you more recent results where actually the randomness of the microstructure is introduced. This is an n by n, and the n for us here is going to be 10 or 12 cells, okay? So it's 1,000 or whatever, 12 cubed cells, and is generated using a program called Surface Evolver. It's not exactly the same as the foam that we tested, but it has the same characteristics, and it's a long story to explain to you why. Okay, it's a random cell, but it's monodispersed. This is what the cell looks like, and we test those cells with beams that have the necessary geometry and material properties, and then we crash it, and I am going to show you again another movie. What happened to it? Sorry. So, here now is a movie from the calculation. That's the response, and this is where we are, okay? And I hope you see, okay, I hope you see that we have, I've gone a little too far, but we have crashed cells and uncrashed cells, and this is, we're already an average strain of 40% here, okay? And you continue, and then you are going to densify the material, and the response now is that essentially the material is behaving in a stable manner. This is as big a calculation as we have done. Okay, it's very significant. Requires significant computer time. It's elastoplastic. It's large deformation. It is beams, but because of size, and in order to limit the extent of crashing, you have to have appropriate contact algorithms that capture the phenomenon. All right. And how good it is shown here. Now you're going to tell me, you're saying that if you model it very carefully, put the proper constitutive model for the base material and the contact and everything else, you can reproduce it. That's what I am saying. But we are looking for something a little bit simpler, because this is a huge calculation. And there is some, okay. Again, just a little bird's eye view, like I said, for each problem. This is a different problem. It's something that we studied in the 90s, and it has to do with compressive failure of fiber composites. I have put up there Argon and Budiansky, who understood the underlying mechanism for the onset of the instability, and so it's fiber composite with a polymeric matrix. Okay, this work basically was done for the U.S. Navy, who in the 90s, in their infinite wisdom, they thought that they would be making submarine hulls out of composite. The composite in compression has a strength that is only 60% of that intention. The reason is that the mechanism of failure are different. In tension, the strength, say, I don't remember now in gigapascals, but it's 300 delta, say 1,000 psi. In compression, it's 180, and in tension is due to failure of the fibers. In compression is due to kinking of the fibers, and kinking is this thing here. What is the mechanism? The mechanism is the following. You compress this, and it tends to develop microbuckling. This is a problem that goes back to the 60s, microbuckling. But the microbuckling is not elastic. The reason it's not elastic is because the matrix is not linear, it's non-linear, and let us say we can call it elastoplastic. The shear response of the material is like this. Okay, this is measured shear response of the material. So if there is a plastic bifurcation that leads to this microbuckling at a very high stress, but because there is always some small misalignments of the fibers, and that's really what this model is showing. It's showing to you an idealized composite with fibers and matrix that you compress, and if you put that shear response in here, you just do equilibrium in here. Theta naught is the initial angle of misalignment, gamma is the additional shear that you get, and this is the axial stress, and this leads to a limit load. This is this is nonlinear, and this is geometric nonlinearity. This leads to a limit load. That's really what's behind the onset of failure, and the fibers bend locally, and once they reach a certain amount of curvature, they break, and this is a clean king bend. This breaking that occurs, in a minute you will see why, is a catastrophic failure, so if it's totally uniaxial, and you just compress it in a simple way, you are going to, it just simply blows up. But if you constrain it, let us say that it's a laminated composite, and it has protection on either side of fibers that are not in the zero direction, and they can take more load. If you do that, then it will fail, and it will develop a king band like you see here. This is a king band that developed in a constrained situation, and if you continue to have that constraint, then you compress it, then it tends to propagate, and I'll show you how it does. Okay? So, it's a very catastrophic failure, but if you're able to constrain the material and limit the extent of the damage from the king bands, then it tends to propagate. This is a very interesting phenomenon because generally speaking, composites are thought to be brittle. They are brittle, but not totally. So let me, I'll show you this, maybe a movie. So, this is an experiment in which we loaded it, and then it failed, and this jump is due to the failure, and let us say that we have ended up with this king bend. It's protected on either side, that's why it has survived. Now, if you continue compressing it, okay, in this case we unloaded and reloaded, no need to go, okay, you see that the band sharpens, and I hope you can see that it is widening, it's broadening and broadening, and while that is going on, this is a flat plateau. Okay, now, and if you look at the so these are straight fibers, and these are bent, these are inclined fibers. So if you look at the transition here, what's happening is that you are feeding in fibers you are bending them locally here with a little curvature, bending them, and when they bend enough, they break, and you see these breaks that propagate, and that's really what's in here, a bunch of breaks. I have a movie, but it's better if I move on. Regarding the onset of failure, this is a model that we did the mid-90s, where we have fibers. It's a 2D version, there is a 3D one also. Fibers that are elastic and a matrix that is elastoplastic. We have put a waviness as an imperfection, and we compress it. If you compress it, this is what you get. Stress, this is shortening. I don't know if you're used to instabilities, but this is as bad as instabilities get. Okay? You reach this point, and you are either controlling the load or you're controlling the displacement in any physical situation. And so whatever you're controlling, this guy is going to jump here. Okay? And that's why the first failure is catastrophic. But you see what happens to the fibers. Okay? They are bending. When we reach here, they start bending. And this bending keeps rotating, okay? The band keeps rotating and develops as you see by the time I come here. And it's okay. I have enough power, I think. And what happens is that when they bend sufficiently, they break. We don't have the breaking in this model. Okay. Now, if you want to see that propagation, and definitely this problem requires more work. Okay, so if you want to see the propagation, we'll develop a different model. Again, it's a brute force model where the fibers and the matrix are modeled in a 3D setting that you see here. You're seeing the top of the specimen, okay, with the proper properties, and with some details that I'm leaving out. If you compress it, you come up and then you come down, and then you see it propagating. Again, we don't have the breaking, but everything else is being reproduced. In other words, this rotation that you get and this angle that we introduced in the model. So this is a very challenging problem, and this kinking is not is a phenomenon that actually appears in a lot of physical systems. It appears in rocks, geological materials, and it appears in wood. So basically, kinking occurs in materials that are highly aligned, and you have anisotropy and nonlinearity in shear. So this is some more recent experiment from one of my master students, French master student for those that are interested in nationalities. And what it is, balsa wood is that lightweight material. The fibers are aligned this way. We compress, okay, stress, change in length. And what happens is that there is a failure. I'll show you what the failure is in a minute. And then you see this extended plateau, and it continues. And if you manage to crush all of it, then it will go up. Now, this specimen, I cannot even read it myself. It has a relatively small, something like 6% relative density. Balsa wood is so light because they cut the wood, they dry it. It has tubular microstructure. I'll show it to you in a minute. And they dry it, and the water is removed. So you only have about 6% of wood material there. Okay, and what happens is that by the time we have come here, we reduce the height by 30%, and it looks like not very much has happened. It's because that little bit of material that's there has been highly compacted, and there's just been a few splinters coming out of the specimen. But the key here is this instability that is occurring here, and then the extended plateau. The behavior is similar. I don't have analysis for this problem. I just have a few things. This is the microstructure. It's like all natural things, is complicated. Okay, these tubes, they are not really they're tubes, but kind of they're of limited length, and there is one after the other. There is their length. Okay. Less than a millimeter long. This is their diameter. Okay, this is their thickness, and they're kind of oriented in the vertical along the growing direction. This is what they look like. But there is other things in this material. There are some other things that are coming radially from the center of the trunk, and they are called rays, and they penetrate these oriented fibers, and they cause some misalignment. So I have stiff fibers, and I have misalignment, and that's really the cause of the failure. If you go in and you look, what you see depends a little bit on the relative density. So this is 3 different densities of the material. But you see here, this is you see it's kinked, but it's not. These are not single solid fibers. They are tubes, and as a result, if you zoom in this failed material, they have crashed in a concertina manner. I don't know if there is a lot of structures people here, but this is reminiscent of what happens in tubes. And by the way, these tracheids, they're almost hexagonal in cross-section. So very similar to what happens in hexagonal honeycombs when you crush them laterally. The mechanism, but that's the local mechanism. There is another more global mechanism that's due to the misalignment that is causing the kinking. I hope that and actually if you measure the shear response and you use this same formula, you can get some pretty good estimates considering the complication of the material, pretty good estimates of the strengths. That's as much as we have done, okay? If there is some bright students here that are interested, I'm looking for a very good one to work on this problem. Okay, now I will talk a little bit about Luther's bands. Very different phenomenon, but Luther's bands is a phenomenon that occurs, let's say, primarily in low carbon steels. You see the behavior, okay, this is a stress, strain. It is the same if you do tension or compression. Okay, the upper yield stress, and then seemingly plateau here is not totally plateau, but relatively constant stress of a certain extent, and then hardening behavior. I didn't go very far. Now, the phenomenon was studied actually extensively in the 50s and 60s. My favorite paper is in the first volume of JMPS. Lomer, I think, is the name. He had the similar pictures, but we have DIC now, digital image correlation, and we have computers. Those guys didn't have; they had to work harder. But he had very similar. So I'm not really discovering anything here, but I am showing to you what happens along this plateau with modern visualization scheme. So this is the specimen. This is the strain that corresponds to these colors, and you can see that okay, the dark blue, okay, is down here. It's at this point, and this green yellow is somewhere here, okay. It's around about 3%. So what we have coexistence of two deformation regimes. This is around 3%. That is around 0.2%. And as we deform this, there is a front separatum. It's an inclined front because this is a strip, and it propagates until the whole thing is consumed. This is the cleanest version of this problem. Okay, it can be more involved, But basically, I want to tie in with the other problems that we have, and instability. Now, of course, the instability here is dislocation driven. I'm not going to go into the details, but if you go and read Cottrell and Belby, 1948, they explain what it is. Okay? And I hope that, like I said, that you can see that is related to the other problems. Back in 2000, we did the following calculation. Again, it's a discrete person, like I said. So this is a finite element, a model with a very fine mesh. And what we did is we buried the complicated physics into, and maybe you guys will call this homogenization, but I don't. We buried it into a simple constitutive model, elastoplastic model, but over here, over the extent of the Luther spans, we introduce a negative slope. Okay, how big is the slope, the negative slope, and so on? It's a detail, but that's what we did. And what you can do then is you can, with just that, it's a little more than that, but I think that's really the essence of it. You can reproduce the phenomenon numerically. So this now is a finite element model. It's the newer version of the same calculation of my later PhD student. But you can see that with just that, okay, you get the initiation. It's a band with a particular orientation. The orientation is plus minus 55 degrees. For you guys that are theoretical, this is known as the heel angle, and there is two characteristics, and it's along one of those characteristics, and then it propagates, as you can see. That is a little dirtier than I'm showing to you here because some other things are involved, but in essence, I wanted to show you that the story can be reproduced. Okay, the more I have studied this,
we have 50 minutes.
No.
I believe you.
We started at 10 after. Yeah. All right. I need another 5. So I have a practical side, okay, to my research, and that is bending of pipes made out of steel. This is something that has to do with the offshore industry. We're in the oil business in Texas, and I have done some work on this. So what happens if I have a tube and I bend it? And as Professor Loco says, when you bend it, it ovalizes. But mine is elastoplastic, and on top of that, I have Luther spans. So that's the question, and I am going to show you what happens in the experiment. This is the moment now. I'm bending it. Is pure bending moment, and this is the rotation of the ends. Remember, the material has a plateau in the stress-strain curve. It became a plateau in the moment, okay? And during this plateau, what happens is that we have a localization, but it's a structural localization. The curvature gets larger in these two locations, and I have coexistence of high curvature and low curvature. This curvature here is at this point, and this curvature is at this point. And as we go on, the two regimes move in, the two high curvature regimes move in, and then at the end we have this. Uniform again. start uniform, end up with uniform, plateau in the middle, but in a moment. You see here the two different curvatures. I am going to just tell you that what happens if you put that kind of stress-strain curve in the material of the structure. So here I am with another movie. All right. This is a finite element model in which you have put that stress-strain curve and it's being bent. I'm going to show it again. Skip. So, the bright color is Luther spans forming, but they are forming in a particular way. They're bands that are happening on the tension and compression. They're kind of like this on top, okay? And they're propagating in this fashion. Behind, the tube is ovalizing, and it is also wrinkling. It has higher curvature over the green, and blue it's lower curvature. And it's propagating, and it goes on and on until all of it is deformed. There is a periodicity that is due to the wrinkling, but the key is that now is uniform deformation and good behavior. I think I am going to close there. I am going to show you one last thing, 3 minutes, that relates to this problem. This is a shape memory alloy. And what we have been doing, is bending little shape memory alloy tubes. What you see here is the stress-strain relationship of the shape memory tube in tension. It's better to see the movie. It's better to see the movie. I know you're hungry, just give me a couple of minutes. So, I hope you saw that there is a propagating instability. I think it's probably better if we went back. Can do that on the movie. So what happens is the red color is highly deformed, the blue color is relatively undeformed, and the phenomenon here is phase transformation, but micromechanically it's related really to the Luther spans. If it was a strip, we would have a band that is propagating in an inclined fashion. It's a tube, and the band now has become into fingers, and it propagates and consumes the tube, and at the end okay, so we are mostly austenite now, to those that know enough about these materials. And now we are going back to martensite. Okay? So my last slide is, the question is, what happens if we bend this tube? This is a little tube. That's what happens if you bend the tube. Again, elastic behavior, a plateau. And during the plateau, if you notice, there is coexistence of two curvature regimes. I am not showing to you the unloading, but the unloading another plateau during which the two curvature regimes show up again, and then of course we're able to close the loop because this is a pseudoelastic material. This is a problem that requires solution, and we don't have one. I think I'll stop there and let you go to lunch. Thank you.
We will wait for lunch.
Okay, you're the boss.
During your talk, you addressed the question whether it's possible to deal with this problem of continuing mechanics. And the answer is yes. With my student company, we studied several forms, polymeric forms. Just with the one-dimensional model with the Ericsson type energy that we showed, we were able to reproduce not only the curve, but also the unloading curve, which is not just showing in the last slides. And not only that, but adding some viscosity. We went into details of these curves, and adding some damage, we were able to reproduce a single behavior. So the very simple one-dimensional model, because when you crash, it's not important what happens in horizontal planes. It can be supposed to be uniform in terms of expression. So our model can be one-dimensional.
Yeah.
And we had a depressive agreement to the experiment.
Well,
it's possible.
As you saw, I did the same thing in other problems, right?
Yeah.
It is possible, but the key question is, how are you going to generate that response? Right? You have to generate it and then input it into your continuum, and that's really well, but this is not a simple game. Well, I agree. It's possible. Yeah.
Thank you for the nice presentation. But almost, let's say, these propagating instabilities are planes. Did you observe some kind of, let's say, non-plane propagations?
There were a number of that are not planar.
Yes, I mean that, for example, when you have something like different shape instabilities.
Yes, if you crash it differently, you're going to get other patterns. But then you see the bending here?
Yes.
That's it, fully 3D.
Yeah. In the case,
The tube?
there is experimental works by Chip in some tension of tubes made of...
Yes. Yeah, he saw the same. Yeah, he saw the same. Sure.
In one of your slides, when you were talking about balloons, I noticed a graph in which, if I'm not wrong, there were a bifurcation after a limit point. I want just to ask, Which phenomena are related both to the limit point and the bifurcation point?
I can see that you're tuned in. In the balloon, there can be a bifurcation. There is bifurcation after, for my material, after. If it's a different material, the bifurcation can be a little bit before. But that bifurcation, for the early one, it basically leads to some asymmetry in the bulge. Instead of being axisymmetric, it may be a little bit non-axisymmetric. And if you inflate it a little bit more, it recovers. It's a temporary disturbance. You understand?
Yes. Because
in my case, the bifurcation is afterwards. Okay.
Because in novel by M&MoCS, it was shown that in particular cases where non-linearities in material behavior are involved, you have to have bifurcation after. No? I think that this is a good point to continue modeling of some phenomena as the one of the balloon show.
Yes, we are in agreement. Perfect, yes.
So it's more a comment than a question. It's about the instability. So it's rather one level, it's not a matter of instability.
Which one?
The Wheeler's phenomenon.
No.
So it's not a nice fact instability, but it's more related to asymmetries of from solid atmospheres. So it's a matter of and diffusion of solids.
You understand the physics. You understand the physics. But you see, what I showed is what simple model can do to reproduce the global behavior. I didn't claim to have reproduced the physics. The physics are complicated.